So today we're going to discuss precipitation reactions and how to do stoichiometry involved with precipitation reactions. So let's talk about what is a precipitation reaction. And they're also known as double displacement reactions because both compounds are displaced or they both switch partners. Precipitation reactions occur when two solutions are mixed and an insoluble solid, what we call a precipitate, forms and separates from the solution. So you take two solutions, put them together, and then usually it's some sort of precipitate that forms at the bottom. To determine the potential products of this type of reaction, we have to break reactants up into their ions and then switch the partners. So for example, let's look at the reaction between potassium chromate and barium nitrate. Okay, if they're both aqueous, that means they're all going to break up into their ions. And so that means that we have the potassium ion, chromate ion, the barium ion, and the nitrate ion. Okay, so what we're going to do is make all possible combinations that aren't already reactants. So what this means is we've got to find a cation and an anion to put together. Can't put together two cations or two anions, but it can't be a compound that already exists as reactant. And so that really limits our choices. Once you've found your combination, also make sure that you check charges to make sure that things are neutral compounds. And so, for example, if we take our potassium ion, well, it's already mixed with the chromate as a reactant, so we need another anion for it to go with. The only one is the nitrate. And I like to write the charges because that helps me ensure that I'm writing a neutral compound. If potassium is +1 and nitrate's a -1, then it's neutral. So let's take our other cation, which is the barium, and the only thing left for it to combine with is the chromate, since it combined with the nitrate as a reactant. And since it's a -2, that's also a neutral compound. Okay, so our two products are potassium nitrate and barium chromate. Well, now we need to figure out which one, if any, is the precipitate or is the insoluble compound, and then which product is soluble or will break up into its ions or is aqueous. And so in order to do this, we use what are called solubility rules. There's a list of solubility rules in any textbook, and I've also got one in the notes. So let's look at some solubility rules. Well, most nitrate salts are soluble, and so our product, potassium nitrate, is going to be soluble. We also know that most chromate salts are only slightly soluble, so we're going to call that insoluble, making barium chromate the precipitate. So when we write our reaction, we've got our potassium chromate plus our barium nitrate, those are both aqueous, and then we've got our two products, our potassium nitrate, which we said was aqueous in this case, and our barium chromate, which is the insoluble compound or the solid. And then we also just balanced it to make sure it was a correctly written chemical equation. Okay, so here are some general solubility rules. So basically all salts of group 1A and ammonium salts are all soluble. All acetates and nitrates are soluble also. So that's where our nitrate came in, being soluble. All binary compounds of group 7A, so the halogens, other than fluorine, with metals are soluble unless we have the metal silver, mercury 1, or lead. In that case, those would be insoluble. All sulfates are soluble, except those of barium, strontium, lead, calcium, silver, and mercury 1. And except for the ones mentioned in Rule 1 with the group 1A elements, carbonates, hydroxides, oxides, and phosphates are all insoluble. Now, it's really going to be beneficial to learn these general rules and kind of memorize them because you're not going to be given anything on the AP exam that's going to tell you these. So if you know the general ones, you can usually pick out whether a compound is soluble or not. Okay, so use solubility rules to predict what will happen when the following pairs of solutions are mixed and write the balanced chemical equation. Okay, so let's look at potassium nitrate and barium chloride. Well, first thing I'm going to do is go through and assign charges. I know potassium is a +1 because it's in the first group. Nitrate, I know from my polyatomic chart, and again, that's something you're going to kind of have to commit to memory, is a -1. Now, barium is located in group 2, so I know that it's a +2, and chlorine is a halogen, and it's a -1. So now if I want to write my products, let's take potassium. I know it can't go with this anion because it's already bonded with it as reacted. So that means the only anion left is chlorine. And then my other product is the barium with the nitrate. Now, since nitrate is a -1, I know I'm going to need 2 of those to make it a neutral compound. So now I need to look at solubility. Well, if you remember from the solubility rules, it said that all nitrates were soluble. And so that's going to make this compound aqueous. Okay, I believe it was the first rule that said all common salts with group 1 were soluble. Well, because this is because chlorine is a halogen, that's considered a salt. Potassium is in group 1, and so that's going to make this compound aqueous as well. Okay, so sometimes you will run into reactions where none of the products are precipitates. Okay, in this case, everything's going to be broken up as its ions. Nothing's actually going to bond together to form a solid, and so in this case, we would say no reaction. Now, it does say to make sure it's balanced, so let's just do that real quick. We've got 2 chlorines and 1, so we'll put a 2 there. And that means we need 2 potassiums, and that means we need 2 nitrates, which we have. So it's balanced, although in this case it'd be no reaction. Let's look at another one. So we have potassium hydroxide again, assigned charges. Now, iron's a transition metal, so I don't know the charge, but I do know nitrate's a -1. And since there's 3 of them, I know it has to be a +3. So now let's switch our partners. So let's take our potassium, and now we need to combine it with the NO3, since we have +1, -1, we're all set there. And then we've got our iron, and our hydroxide's a -1, so I know I need 3 of them. Well, I know that any nitrate is soluble, so that's an AQ. Now remember reading something about hydroxide? And so any hydroxide, unless it's mixed with the group 1A, is insoluble. Well, iron is not a group 1A metal, and so that makes iron hydroxide a solid. Now, where's my pen? So we'll make that an S. Okay, the last thing we need to do is make sure it's balanced. So we have 1 potassium, 3 nitrates, 1 nitrate, so I'm going to put a 3 out front. That changes my potassiums, which changes my hydroxides. And since I already have 3 as the product, I'm all set and it's balanced. Okay, we know the aqueous solutions usually break up into their ions, so that's why we get the AQ. So what this means is that the formula equation, the one that we just wrote in the example, is not really accurate because it's showing the compound together even though it's aqueous. And so what we need to do then is come up with another way to represent that. So here's our formula equation. Okay, we need to write what's called the complete ionic equation. This shows everything as it actually is. If it's aqueous, it's broken apart. If it's a solid, it's staying together. And so what that means is when we break things apart, because we have a potassium with the chromate, we have 2 down here, meaning 2 potassiums. So when we write them as the ions, we want to put 2K plus, because then now it's 2 potassium ions. And then we have our chromate ion. And barium nitrate is also aqueous, so we have our barium and our 2 nitrates. Remember, this 3 belongs with the nitrate. That's one whole thing. Okay, now we go to our products. We have 2 potassiums because of the 2 out front. Because the 2 is out front and applies to the whole compound, we also have 2 nitrates. And then barium chromate is a solid. It's not going to break apart into ions, and so we're going to reflect that by keeping it together. Okay, then we need to write what's called the net ionic equation. This includes only the components that are involved directly in the reaction, the ones that are actually producing the precipitate. The rest of the ions are called spectator ions. They're kind of just there, but they're not really contributing to the product. And so the way that we identify those is by looking at our complete ionic equation and canceling out things that are exactly the same on both sides. So for example, we have 2 NO3s, and there's spectator ions. They're not changing, they're not doing anything. We also have 2 potassium ions on both sides that would be considered spectator. Now, the chromate and the barium are bonded together on the product side, and so we don't want to take those apart. So now we write down what's left. So we have our chromate and our barium, and that goes to our product. And if you notice, our equation is balanced because we balanced it up top. So you should end up with a balanced equation. If you don't, or you have extra things involved, then something went wrong and you should probably go back and check it. Okay, let's look at an example. So for the following reaction, write the formula equation, the complete ionic equation, and the net ionic equation. Okay, aqueous potassium hydroxide is mixed with aqueous iron 3 nitrate. Now we did this one before, but let's do it again real quick. So we have potassium hydroxide, +1 -1, so it's neutral. It says it's aqueous. Okay, it's good to be able to write the compound from the word, so this is good practice. Okay, it's mixed with, so we put a plus. Aqueous iron, Roman numeral 3 means it's a +3. Nitrate is a -1, so I need 3 of them to make it neutral. That's also aqueous. Okay, first thing we need to do is predict our products. So let's take our potassium and combine it with our only available anion, which would be the nitrate. +1 -1, it's neutral. I don't know if it's aqueous or not yet, so we're going to get to that in a second. Moving on to the next one, we have iron, and the only available anion would be the hydroxide. It's a -1, so that means that I need 3. Now, if you remember from the solubility rules we talked about before, anything with nitrate is aqueous. Hydroxides are insoluble unless it's a group 1A metal. Iron is not, and so it becomes our solid. Last thing we need to do for this step is balance. I know I have 3 hydroxides, so I need 3 there. That makes 3 potassiums, which makes 3 nitrates. I have 3. Now I'm balanced. That is the formula equation. Okay, now I need to move on to the complete ionic equation, which means I'm going to break apart anything that's aqueous into its ions. Potassium hydroxide is aqueous, so we have 3K plus 3 OH minus, because that 3 applies to the entire compound. Plus I have my iron and 3 nitrates. Potassium nitrate is also aqueous, so we have 3K plus 3NO3. Now, iron hydroxide is a solid, so I'm not going to break it apart. I'm going to leave it together. And that's our complete ionic equation. It's showing exactly what's in the beaker, basically. Okay, now to write the net ionic equation, we're going to cancel out our spectator ions. NO3 is a spectator ion. Potassium is a spectator ion. I'm going to write down what's left. So I have my hydroxide plus my iron. And that's going to give me iron hydroxide. Okay, it's balanced. I've got only the components that contribute to the solid. That's my net ionic equation.